Hi everyone, and welcome to our video on the bicarbonate buffer system. Proper physiological functioning depends on a very tight balance between the concentrations of acids and bases in the blood. Acid-base balance is measured using the pH scale. A variety of buffering systems permit blood and other bodily fluids to maintain a narrow pH range, even in the face of perturbations. A buffer is a solution that minimizes the change in pH when a base or an acid is added to the solution. Most buffers consist of a weak acid, which releases hydrogen ions, and a weak base, which binds hydrogen ions. If an acidic solution is added to a buffer solution, the buffer will combine with the extra hydrogen ions and help maintain the pH. If a basic solution is added to a buffer solution, the buffer will release hydrogen ions to help maintain the pH. There are many different buffers, and each one stabilizes the pH of the solution within a specific pH range. One buffer may be effective within a range of pH 2 to pH 6, while another buffer may be effective within a range of pH 10 to pH 12. A strong acid completely dissociates all of its hydrogen ions in water. A weak acid partially dissociates in water. These acids are very efficient at preventing pH changes. Strong bases dissociate easily in water and quickly tie up hydrogen ions. Weak bases accept more hydrogen ions. The buffer systems in the human body are extremely efficient, and different systems work at different rates. It takes only seconds for the chemical buffers in the blood to make adjustments to pH. The respiratory tract can adjust the blood pH upward in minutes by exhaling CO2 from the body. The renal system can also adjust blood pH through the excretion of hydrogen ions and the conservation of bicarbonate, but this process can take hours or even days to have an effect. The buffer systems functioning in blood plasma include plasma proteins, phosphate, bicarbonate, and carbonic acid buffers. The kidneys help control acid-base balance by excreting hydrogen ions and generating bicarbonate, which helps maintain blood plasma pH within a normal range. Protein buffer systems work predominantly inside cells. The three main buffer systems in our bodies are the bicarbonate buffer system, the phosphate buffer system, and the protein buffer system. Let's look at them in more detail. The bicarbonate buffer system is an acid-base homeostatic mechanism involving the balance of carbonic acid, bicarbonate ion, and carbon dioxide in order to maintain pH in the blood and duodenum, among other tissues, to support proper metabolic function. Catalyzed by carbonic anhydrase, carbon dioxide reacts with water to form carbonic acid, which in turn rapidly dissociates to form bicarbonate and a hydrogen ion. As with any buffer system, the pH is balanced by the presence of both a weak acid and its conjugate base, so that any excess acid or base introduced to the system is neutralized. Failure of this system to function properly results in acid-base imbalance, such as acidemia, which means a pH lower than 7.35, or alkalemia, which means the pH is higher than 7.45 in the blood. In tissue, cellular respiration produces carbon dioxide as a waste product. As one of the primary roles of the cardiovascular system, most of this CO2 is rapidly removed from the tissues by its hydration to bicarbonate ion. The bicarbonate ion present in the blood plasma is transported to the lungs, where it is dehydrated back into CO2 and released during exhalation. These hydration and dehydration conversions of carbon dioxide and bicarbonate, which are normally very slow, are facilitated by carbonic anhydrase in both the blood and the duodenum. The bicarbonate ions serve to neutralize acids introduced to the blood through other metabolic processes. Likewise, any bases are neutralized by carbonic acid. As calculated by the Henderson-Hasselbalch equation, In order to achieve the normal pH of 7.4 in the blood, a 20:1 ratio of bicarbonate to carbonic acid must be maintained. This homeostasis is mainly mediated by pH sensors in the medulla oblongata of the brain via negative feedback loops to effectors in the respiratory and renal systems. In the blood, the bicarbonate buffer system is coupled to the lungs via respiratory compensation, the process by which the rate and/or depth of breathing changes to compensate for changes in the blood concentration of CO2. By Le Chatelier's principle, the release of CO2 from the lungs causes carbonic anhydrase to form CO2 until all excess protons are removed. Bicarbonate concentration is also further regulated by renal compensation, the process by which the kidneys regulate the concentration of bicarbonate ions by secreting hydrogen ions into the urine, while at the same time reabsorbing bicarbonate ions into the blood plasma or vice versa, depending on whether the plasma pH is falling or rising. The respiratory system contributes to the balance of acids and bases in the body by regulating the blood levels of carbonic acid. CO2 in the blood readily reacts with water to form carbonic acid, and the levels of CO2 and carbonic acid in the blood are in equilibrium. When the CO2 level in the blood rises, as it does when you hold your breath, the excess CO2 reacts with water to form additional carbonic acid, lowering the blood pH. Increasing the rate and/or depth of respiration, which you might feel the urge to do after holding your breath, allows you to exhale more CO2. The loss of CO2 from the body reduces the blood levels of carbonic acid and thereby adjusts the pH upward toward normal levels. As you might have surmised, this process also works in the opposite direction. Excessive deep and rapid breathing, as in hyperventilation, rids the blood of CO2 and reduces the level of carbonic acid, making the blood too alkaline. This brief alkalosis can be remedied by rebreathing air that has been exhaled into a paper bag. Rebreathing exhaled air will rapidly bring blood pH down toward normal. The chemical reactions that regulate the levels of CO2 and carbonic acid occur in the lungs when blood travels through the lungs' pulmonary capillaries. Minor adjustments in breathing are usually sufficient to adjust the pH of the blood by changing how much CO2 is exhaled. In fact, doubling the respiration rate for less than 1 minute would increase the blood pH by 0.2. This situation is common if you are exercising strenuously over a period of time. To keep up the necessary energy production, you would produce excess CO2. In order to balance the increased acid production, the respiration rate goes up to remove the CO2. This helps to keep you from developing acidosis. The body regulates the respiratory rate by the use of chemoreceptors, which primarily use CO2 as a signal. Peripheral blood sensors are found in the walls of the aorta and carotid arteries. These sensors signal the brain to provide immediate adjustments to the respiratory rate if CO2 levels rise or fall. Yet other sensors are found in the brain itself. Changes in the pH of the cerebrospinal fluid affect the respiratory central in the medulla oblongata, which can directly modulate breathing rate to bring the pH back into the normal range. Hypercapnia, or abnormally elevated blood levels of CO2, occur in any situation that impairs respiratory functions, including pneumonia and congestive heart failure. Reduced breathing, or hypoventilation, due to drugs such as morphine, barbiturates, or ethanol, also result in hypercapnia. Hypocapnia, or abnormally low blood levels of CO2, occur with any cause of hyperventilation that drives off the CO2, such as salicylate toxicity, elevated room temperatures, fever, or even hysteria. The renal regulation of the body's acid-base balance addresses the metabolic component of the buffering system, while the respiratory system, together with the breathing centers in the brain, control the blood levels of carbonic acid by controlling the exhalation of CO2. The renal system controls the blood levels of bicarbonate. A decrease in blood bicarbonate can result from the inhibition of carbonic anhydrase by certain diuretics or from excessive bicarbonate loss due to diarrhea. Blood bicarbonate levels are also typically lower in people who have Addison's disease and in people who have renal damage. Finally, low bicarbonate blood levels can result from elevated levels of ketones, which is common in unmanaged diabetes, which bind bicarbonate in the filtrate and prevent its conservation. Bicarbonate ions found in the filtrate are essential to the bicarbonate buffer system, yet the cells of the tubule are not permeable to bicarbonate ions. The following steps are involved in supplying bicarbonate ions to the system. First, sodium ions are reabsorbed from the filtrate in exchange for hydrogen ions by an antiport mechanism in the apical membranes of the cells lining the renal tubule. Second, the cells produce bicarbonate ions that can be shunted to peritubular capillaries. Third, when CO2 is available, the reaction is driven to the formation of carbonic acid, which dissociates to form a bicarbonate ion and a hydrogen ion. Fourth, the bicarbonate ion passes into the peritubular capillaries and returns to the blood. The hydrogen ions are secreted into the filtrate, where they can become part of a new water molecule and be reabsorbed as such or removed in the urine. It is also possible that salts in the filtrate, such as sulfates, phosphates, or ammonia, will capture hydrogen ions. If this occurs, the hydrogen ions will not be available to combine with bicarbonate ions and produce CO2. In such cases, bicarbonate ions are not conserved from the filtrate to the blood, which will also contribute to a pH imbalance and acidosis. The hydrogen ions also compete with potassium to exchange with sodium in the renal tubules. If more potassium is present than normal, potassium rather than hydrogen ions will be exchanged, and increased potassium enters the filtrate. When this occurs, fewer hydrogen ions in the filtrate participate in the conversion of bicarbonate into CO2, and less bicarbonate is conserved. If there is less potassium, more hydrogen ions enter the filtrate to be exchanged with sodium, and more bicarbonate is conserved. Chloride ions are important in neutralizing positive ion charges in the body. If chloride is lost, the body uses bicarbonate ions in place of the lost chloride ions. Thus, lost chloride results in an increased reabsorption of bicarbonate by the renal system. The first equation shown in this slide is a modified version of the Henderson-Hasselbalch equation, which can be used to relate the pH of blood to constituents of the bicarbonate buffer system. In this equation, pKa H2CO3 is the negative logarithm of the acid dissociation constant of carbonic acid, and it is equal to 6.1. HCO3 is the concentration of bicarbonate in the blood, and H2CO3 is the concentration of carbonic acid in the blood. When describing arterial blood gas, the Henderson-Hasselbalch equation is usually quoted in terms of PCO2, or the partial pressure of carbon dioxide, rather than H2CO3. However, these quantities are related by the second equation shown on the slide, where Kh of CO2 is a constant including the solubility of carbon dioxide in blood. KHCO2 is approximately 0.03. Combining these equations results in the third equation shown on the slide, relating the pH of blood to the concentration of bicarbonate and the partial pressure of carbon dioxide. In these equation, pH is the acidity in the blood, HCO3 is the concentration of bicarbonate in the blood, and PCO2 is the partial pressure of carbon dioxide in the blood. The Henderson-Hasselbalch equation, which is derived from the law of mass action, can be modified with respect to the bicarbonate buffer system to yield a simpler equation that provides a quick approximation of the hydrogen ions or HCO3 concentration without the need to calculate logarithms. This is depicted in the first equation on the slide. Since the partial pressure of carbon dioxide is much easier to obtain than that of carbonic acid, the Henry's law solubility constant, which relates the partial pressure of gas to its solubility for CO2 and plasma, is used in lieu of the carbonic acid concentration. After solving for hydrogen ions and applying Henry's law, the equation becomes the second formula presented, where K is the dissociation constant of carbonic acid, which is equal to 800 nanomoles per liter. After multiplying these constants and solving for HCO3, the equation is simplified to the third one shown on the slide. Let's review some key concepts from this video. A variety of buffering systems exist in the body that help maintain the pH of the blood and other fluids within a narrow range, namely between pH 7.35 and 7.45. A buffer is a substance that prevents a radical change in fluid pH by absorbing excess hydrogen or hydroxyl ions. Most commonly, the substance that absorbs the ion is either a weak acid, which takes up a hydroxyl ion, or a weak base, which takes up a hydrogen ion. Several substances serve as buffers in the body, including cell and plasma proteins, hemoglobin, phosphates, bicarbonate ions, and carbonic acid. The bicarbonate buffer is the primary buffering system of the interstitial fluid surrounding the cells and tissues throughout the body. The respiratory and renal systems also play major roles in acid-base homeostasis by removing CO2 and hydrogen ions, respectively, from the body. Thank you for watching and have a great day.